Okay, this is the second hour of Physics 1B for November 8th, and we into the last thing to talk about solving this. So I think you all should have had enough time. Can you all put your answers in the chat now, if you want to rank these? And I'll just go through and we'll calculate all of them real quick, too. What is the... And I'm going to get some water while you're typing this. Okay, it looks like everybody got the right answer. 3, 1, 2. That's the right answer. Sorry, I ran out of water. Okay, so... Yep, that's right. Seems like everybody got it right. I don't know if we need to actually calculate it, but let's do it real quick. The first one, number 1, says it absorbs 5,000 joules of heat, rejects 4,500. That means we take 1 minus 4,500 divided by 5,000. That's the efficiency for number 1, and I got 0.1. The efficiency for number 2. And this one you're given work, so it's going to be 2,000 joules divided by 25,000 joules. I think this one was 0.08 maybe. Does that look right to you all? Look at my calculator real quick. And then for number 3, for this one you have to do a little bit of a calculation. So you're given that the work is 400 and it rejects 2,800 joules of heat. So you have to say that the work plus QC is going to be equal to QH. And in this case, that's going to be equal to 2,800 plus 400, which will be 3,200 joules. And then you have to take, there's 2 different ways to do it now, but the easiest one would just be to say that the efficiency is going to be 3,200, right down here, 3,200. Oh no, that goes in the bottom, right? It's the work in the top, sorry. We're using, just to be clear here, hard to keep everything on the page, work over QH. So if it's 400 joules of work, then you do 400 joules of work, that's a 4, divided by 3,200 joules, and that one was 0.125, making it the most efficient. So as you all said, it's 3 is greater than 2 is greater than 1. Okay. So, nice job on figuring that out. Helps to, let me, I'm going to have to move some things around. I apparently didn't leave nearly enough room for myself here. Do like that, that should be plenty of room. Okay, so now we're going to do this problem where we can see what kind of problems you're going to be seeing on your homework a little bit. So, analyzing a heat engine. Too much, just a little bit. So it says, a gasoline truck engine takes in 10,000 joules of heat and delivers 2,000 joules of mechanical work per cycle. The heat is obtained by burning gasoline with a heat of combustion of 5 times 10 to the 4 joules per gram. What is the thermal efficiency of this engine? How much heat is discarded each cycle? If the engine goes through 25 cycles per second, what's the power output in watts and horsepower? How much gasoline is burned each cycle? How much gasoline is burned per second and per hour? A lot of different questions. Let's start off by drawing a picture of what's happening in the system right here. So it says a gasoline truck engine takes in 10,000 joules of heat and delivers 2,000 joules of work per cycle. So we have 10,000, was it 10,000 joules of heat coming in? What is the, what can I call this one? What can I call the 10,000 joules? QH, exactly. This is going to be QH. We got a new thing. When I write H's, apparently we're going to get this little strange line. Okay, so that's QH. And then it says that it delivers 2,000 joules of mechanical work per cycle. So that's our work, right? So we'll say 2,000 joules is going to be the work done by the system per cycle. Now we can find, so this is kind of a picture we can use similar to the picture we had right here, right? In fact, we can maybe move this down a little bit so we can kind of see it as we're doing this. Move it over here, something like that. So we have 10,000 joules of heat, 2,000 joules coming in. So actually we can figure out what this leg here is going to be, right? What's QC going to be in this case? What's QC going to be in this case? 8,000, right? So we can say that the amount of energy that flows into our cold reservoir is going to be 8,000 joules. So that's going to be QC, absolute value, right? Alrighty, so that's our picture. Compare that to the picture on the right over here. So down here we would have our cold reservoir, right? Up here we would have our hot reservoir. Okay. We also are given the fact that the latent heat of combustion is 5 times 10 to the 4 joules per gram. Part A says, what is the thermal efficiency? E. Well, we can get that pretty easily by taking the amount of work done by the system and dividing by QH. So that's going to be 2,000 divided by 10,000. These are both in joules, so we don't really need to write the unit since it's a ratio, but we can anyway. Looks like we're going to get an efficiency that's equal to, what is it, 0.2? 20%. Pretty easy. All right, part B. Part B says how much heat is discarded each cycle. We already figured that out by doing 10,000 minus this, but let's write it down as an equation so it's clear where it came from. We know that the work done by the system is equal to the difference in the heat that comes in minus the heat that comes out, minus like this. If we put absolute value signs on both of these, that means that QC should be equal to W minus QH. We do a little algebra, and that means that QC is equal to 10,000. Nope. Hold up. That's not how you do algebra. Sorry. QC should be equal to QH minus W. So it's going to be 10,000 joules minus 2,000 joules. In this case, I do need to write the unit here. I'm mentioning this because a lot of people lose points on their exams in this class because they just don't think units are required. And I don't know where you got that idea, but the only time you don't need to write a unit is if you have a ratio, and the units are going to cancel anyway. And even then, you might want to just write it since you're students, and just in case. Okay, so QC is 8,000 joules. Let's keep going. Part C. If the engine goes through 25 cycles per second, what is the power output in watts? So what do we need to do to figure this part out? We know that it delivers 2,000 joules of mechanical work per cycle, and in part C it's saying it goes through 25 cycles per second. Use power equal to work divided by time. Uh, 2,000 times 25 is the right answer. And Richard, you're correct that power is work divided by time. In this case, it's going to be work multiplied by frequency, though, because in this case we don't have time. I guess you could say it's 1 over 25 seconds per cycle. I guess you could write it like that if you want to. Right, so basically we're going to be saying that the amount of power output should be equal to, let's do it that way, work divided by time, and then we'll just say that the time in this case is going to be equal to 1 over 25. It's 1 cycle per 25 seconds. And then we can say that that means that the power in this case is going to be equal to the work, which is 2,000 joules per cycle. Multiplied by 1 cycle every 25 seconds. I always like to think about these things as really just conversion factors, right? We have 2,000 joules per cycle, 1 cycle per 25 seconds. You can get to joules per second, which is what power is. So, no, wait a minute. Wait, did I confuse myself? it's 1 second. This is upside down. This is upside down. I tried to use your equation and it just failed hard. Apologize. We're just going to do this the way that I wanted to do it. Okay. What we have is that the rate, I'm just going to call it the rate, in this case, is 25 cycles per second. And then we're just going to do a conversion factor now. Now we can take, if this is the rate, we can copy this one and put it over here. Well, let me do that. And there we go. Now it cancels out properly and we get to the 2000 times 25, right? There we go. Okay, apologize for that. Sorry for the mistake there. I got confused. So 2000 times 25 is going to be, well, 25 times 2 is 50. Should be 50,000. Yeah, 50,000 watts, because joules per second is watts. There we go. Okay, if I had written down the time correctly, we could have used Richter's equation, so that is the right way to do it. That's in watts. We want to get it in horsepower, and the conversion from watts to horsepower, I think is like something like 746 watts is equal to 1 horsepower. Maybe you all can check that out. Tell me if it's right or wrong. That means that we can get the power to be equal to 50,000 watts multiplied by 1 HP divided by 746 watts. To put that one in the calculator. You do 50,000 divided by 750, that'd be pretty easy. Oops, 746. Okay, we're going to get 67 horsepower. That's going to be the power output. Okay. Pretty easy so far. Any questions so far? All right, now for the part that gets a little trickier. It says in part D, how much gasoline is burned in each cycle? So we know that the latent heat of combustion for gasoline is 5 times 10 to the 4 joules per gram, about 50,000 joules per gram. And the question is, how much is burned per cycle? So what quantity would we want to use for that? Which Q are we going to use? Are we going to use Q cold, Q hot, or are we going to use the work done? Q hot, I think that's right, because the idea is that, if you're getting 10,000 joules of energy, it doesn't come from nowhere. It has to be coming from somewhere. So we would assume in this case that the hot reservoir in this case is we're burning gas over here, gasoline, but let's try this gas. We're burning gas in this case. So that's going to be the hot thing that's here, which means for part D, we need to find the QH, basically. If we just take this and we set it equal to the mass of the fuel that we have, multiplied by the latent heat of combustion for the fuel, that should allow us to find the mass of fuel that we burn per cycle. So the mass of fuel should be equal to QH divided by LC. QH is 10,000 joules. We divide by LC, which was 50,000 joules per gram. Now we don't need to do any kind of conversion here because it'll give us an answer that's in grams, and that's totally fine. I think what we're going to get is 0.2 grams. Does that look right? Feels right to me. We're not off the screen. We're fine. That's the answer. 0.2 grams. And then, any questions? Alrighty. And then it says, how much gasoline is burned per second and per hour? Well, if we know that, part E, we know that there's 0.2 grams burned per cycle, right? Then we can take that, 0.2 grams per cycle, and we can multiply by the number of cycles per second. And that will give us 25 divided by 5 is 5. So we're going to get 5 grams per second, right? And then what do they want per hour? How much gasoline is burned per second? 5 grams a second. How much gasoline is burned per hour? If we want to get per hour, we would just multiply by 3,600, I think. So 5 grams per second multiplied by 3,600 seconds per hour, 60 times 60. And 5 times 36. So 5 times 40 would be 200. So 5 times 36 is going to be like 20 less than that, which is 180. So 18000, comma, grams per hour. You all do the math there and tell me if that's right or not. Okay. 18,000 grams per hour. Okay. Relatively easy problem. The key thing for these kind of problems is just understanding what the different things are, you know. What is QH, what is QC, what is W, and just, you know, properly applying things. Okay? 15,000 plus 600 times 5. Definitely a way to do it for sure. Okay. Or you can remember that multiplying by 5 is the same thing as doubling and dividing by 10, which is probably even easier. So you take 3,600, you double it, you get 7,200. Wait, that doesn't work. No, multiply by 10 and then divide by 2. So 36,000 divided by 2, you get 18,000. That's what I'm saying. Okay, so now we're going to get into talking about internal combustion engines and what's called the Otto cycle and the diesel cycle. It's shown right here. Yeah, we're getting really run into things here. We're going to do this problem for sure. We should get to this eventually. Let's just kind of shift them over to the side here so we can have some room to talk about this though. Okay. All right, so next thing we're going to talk about are internal combustion engines. Which we're going to say for short is just ICE. Okay, so an internal combustion engine, I think the easiest way to talk about it is just to look at this picture right here. And to mention some things about what's going on. So first of all, we're going to talk about something called a compression ratio. Okay, so let's just go ahead and define that up here so we can use it as we go. Compression ratio is going to be the amount by which the gas expands or contracts, however you want to look at it. The compression ratio is going to be defined as R, okay? And we're going to say that the volume in our case is going to go from V to R times V. And this is going to be the volume of the gas inside of our container right here, okay? And R is usually on the order of like maybe 8 to 10 for the type of engines that we're going to be talking about to begin with here, okay? Making sure I get it right. Yeah, R is positive. The gas expands in these processes from V to R times V. So from maybe 10 liters to 80 liters, or from 10 liters to 100 liters, right? R is just a ratio of that change. It showed up in some of the problems that we've done actually. So here is our picture of the internal combustion engine cycle that we're going to be using to describe this here. Okay. So this is a cycle of a 4-stroke internal combustion engine. This could maybe be in a car, it could be in a lawnmower, it could be in a weed eater, anything that has some kind of engine inside of it that converts fuel into energy. Okay, so let's go through the steps 1 through 5 here. Okay, so we have an intake valve, and this is what's called the intake stroke. Okay, it says let me expand this so that make sure you can actually read the words that are on here. In the intake stroke, the piston moves down, causing a partial vacuum in the cylinder, and a gasoline-air mixture enters through an intake valve. Okay, so as this moves down, presumably the intake valve is pulled down due to the vacuum that's created. During that period, the exhaust valve is closed so that the working substance, which in this case is the gasoline-air mixture, can't escape. So gasoline and air come into here. The piston moves down. Okay. And then there is a compression stroke where the intake valve closes now. The mixture is compressed as the piston moves upwards. As the mixture gets compressed, eventually, once the compression reaches a certain point, the spark plug is going to fire. Okay? This is where the volume of our system here, the volume in this case is going to be V, and then the volume after this is going to be R times V. So the spark plug ignites the mixture. What's going to happen when you ignite a mixture of gasoline with air? Well, the gasoline is going to create a bunch of heat through its explosion, which is going to cause the gas that's inside of here to heat up. And when gases heat up, they expand. Okay, so this is the power stroke. Okay, maybe I'm wrong with this. It's called the power stroke because this is where the power is coming from, because you've now extracted energy from your mixture of gasoline and air, and that's going to provide the downward motion here. And that expansion is where all of your energy is going to come from. All right. And then the next, so it says hot burn mixture expands, pushing the piston down. And then it says the exhaust stroke. The exhaust valve opens. The piston moves up, expelling exhaust, and leaving the cylinder ready for the next intake stroke where it's going to pull in more gas and air. Obviously, this repeats itself, right? The whole point of this is you want to have a repeatable process. So let's see if this makes any logical sense here. For me, it's a lot easier for me to think about what's happening here, starting from this picture here, because it seems like that's where the energy is coming from, if you know what I mean. So let's look at it from here. You have an explosion. It drives the piston down, but the piston is connected to something that has this rotational nature to it down here, right? And what that means is that when the piston moves down, this... I don't even know what they call this thing right here. Does anyone know what they call this? Those of you that are... what is the thing that's connected to the piston that causes the rotation? What is that called? Is it called, like, I don't know, an actuator or a rotor? Does it have a name? Anyone know? This is... Oh, crankshaft. Here it is. Well, I'm more interested in knowing what this piece is, because the crankshaft is the thing that's then going to connect back to the drivetrain and make the wheels move, right? I don't know. Maybe this whole thing is called a crankshaft. I'm not an expert in this kind of stuff at all, as you can tell. Point is, if we go from here to here, we can imagine that this thing starts to move, right? And even though all the energy came from that explosion, because it's connected to something that can rotate, because it's saying that, yeah, I can see the connecting rod thing here. Because this is connected to something that can rotate, right? Then it's going to continue to rotate due to inertia, right? So there's an expansion that occurs. It drives this thing around, but this little piece has to keep moving, right? And because of the nature of it, it's going to keep moving, and it's going to push up. And in that process, the exhaust valve is going to open, which is going to allow it to expel extra energy, right? And then, again, it has inertia because of this explosion that occurred here, so it's going to keep wanting to rotate, which means it's eventually going to start pulling back down here. And then you can repeat the process, because now you have energy again. This is still rotating. It'll eventually compress back, and you repeat the cycle over and over and over again. And that is that's kind of what's happening inside of a internal combustion engine. I don't think that's a complete picture. This is, after all, a physics class and not an engineering class. We're not learning exactly how to build these things or what the internal, all the pieces of it are. What we want to understand is what kind of energy conversions are happening, how much work is done per cycle, what does the compression ratio have to do with the amount of energy you're getting out of the system. Do you want a large compression ratio? Do you want a small compression ratio? Those are the kind of questions that we want to ask. We'd also want to ask, what's the best type of gas to put into here? You know, what kind of gasoline air mixture is going to be the best? All right. Okay. So we're now going to talk about. Okay. Does anyone have any questions or comments about this before I move on? Any part of this that doesn't make sense to you that you'd like to talk about? We can talk about it. Certainly this doesn't make sense to all of you. Certainly many of you are sitting there thinking, hey, this doesn't make any sense to me. I don't understand step 4. I don't understand 5, or what's going on with the exhaust valve. Anything you want to talk about, we can try to talk about it. I might not have all the answers, but we can at least address the questions and understand that they're questions. So any questions anyone has before we go into talking about the thermodynamics of what's going on here? Okay, so you can understand the idea that the explosion here could make something rotate, and that rotation, through enough proper setup, could suck gas in here and then expel exhaust out here, and so on and so forth. So it's understandable how you can take this explosion and turn it into rotational motion. And once you've got rotational motion, yeah, okay. I understand how the piston moves downwards because of the ignition of the air and gas mixture, but how does it move otherwise? So my best answer to that question, Umair, I believe is inertia. I believe the answer is inertia. Once it starts moving, it kind of has to keep going. Especially, think about if this explosion is really violent, right? If it's really violent, then there's going to be so much energy that's placed into the crankshaft here that it's going to have more than enough energy to complete one revolution before it gets back to the point that it's here and it needs energy to push itself again. Does that make sense? If the explosion's big enough and you're connected to a rotational motion thing right here, it's going to have to keep rotating to get all the way back to that same position. Yeah, it has to keep spinning so the piston gets pumped back up. Exactly. So can you tell from the picture that the piston pushes down this direction, but eventually that downward motion actually causes it to return and push back up? That's kind of the idea, yeah. Really good question, though. I'm glad you asked that question, because I'm sure other people were wondering the same thing. Really good question. Okay, so when I say inertia, I just mean that it's spinning so fast that it can't be stopped spinning, right? Just like a locomotive moving down a set of train tracks, it doesn't just instantly stop moving just because they hit the brakes. It takes time for it to slow down, right? Okay. So next we want to talk about a particular version of one of these engines in of what's going on here. So we're going to be using this right here for what we call the Otto cycle. That's what we're going to talk about now. This is just one of I think this is like kind of an idealized, yeah. It says this is a PV diagram for the Otto cycle, an idealized model of the thermodynamic processes that occur in a gasoline engine. Okay, so do gasoline engines actually operate this way? No, but we have to come up with some way to talk about it so that we can, so that we can do some problems and try to understand how you might improve the efficiency of one of these things, right? So here is the Otto cycle. Okay, do we start at point A? I guess we started at 1. Adiabatic compression, the compression stroke. Where is that? This is the compression stroke, right? So what has to happen during the compression stroke? Well, the volume has to get smaller, right? So the volume goes from R times V, so maybe 8 times the volume, down to the volume of just V. Notice in that process, what happens to the pressure? So we're starting at A, we're going from A to B, right? What happens to the pressure now? Realize that A to B it's 2 to 3, right? Yeah, well, it's basically 2. A to B is number 2, the compression stroke, right? What has to happen to the pressure now? If the volume decreases rapidly from something like 8 times its volume, like let's say it's 80 liters here, and it comes down to 10 liters here, what has to happen to the pressure of the gas inside of here? It has to increase, right? So that's why the slope of this line is going upwards to higher pressures. Notice that it's always important when you look at graphs to look at the axes. This is pressure on the y-axis, and this is volume on the x-axis. This is your standard PV diagram that we've been looking at, right? Okay, so that makes sense, right? Next, from B to C is going to be heating at constant volume. That's where the fuel combustion is going to occur. So at constant volume, this is where it gets to be, it's hard to believe that the combustion is going to occur at a constant volume, but that's okay. We'll just pretend that it does for now. So from B to C along a line of constant volume, this is where the hot energy is coming in from the combustion of the fuel, right? We combust the fuel, that's where our QH comes from. Spark plug fires, lights the fuel on fire, and the chemical energy contained within the molecules of the fuel is released in the form of heat. And as a result, the pressure gets even higher. Because the pressure is even higher, now the system is going to want to expand again. So now we have adiabatic expansion, which is the power stroke. Can you all remind me? Because it's been a week, right? We only meet once a week for this kind of stuff. What does adiabatic mean again? What does adiabatic mean again? No heat transfer, which means what? Q is equal to 0. Exactly. So all of our heat transfers are going to occur along BC or DA, because you'll notice if we go back, step 1 was adiabatic compression. Step 3 is adiabatic expansion. So both of these, the compression stroke and the power stroke, we're going to know are adiabatic, which means Q is equal to 0, which means I think what? Delta U is equal to negative W or something like that, right? Yeah, because delta U is normally equal to Q minus W. So we're going to be needing to use that. So adiabatic expansion power stroke. Okay, so that's number 3 power stroke right here. Hot burning mixture expands, pushing the piston down. Okay, so in that process, of course, the volume will increase because now going along from C to D, our pressure decreases, but the volume increases, which is the place where we're going to get our work done now, right? That's where the work's coming from, is when that volume increase occurs, because remember that work was equal to the integral of PdV, and when volume doesn't change, you get no work, right? So our positive work here is occurring along the line CD. That's where our work is coming from, right? If you remember our diagram where you have QH coming in, right? You have work going out, and you have QC leaving, then the W here is occurring in step 3, right? That's where you're getting your energy from. That's why it's called a power stroke. Finally, we need to return our system back to the original system. The only way for that to occur is for some of the heat to be expelled out of the system, and that's where the exhaust comes in. That's why you have an exhaust pipe on your car, is you need to expel the heat, okay? So in the case of the power plant, we were expelling heat by putting our steam in contact with a cold reservoir. In this case, the cold reservoir is the external air, the surrounding environmental air. That's the cold reservoir. Just the air that's out here that can absorb as much energy as you want to, right? Because it's the environment. There's plenty of, So we expel the cooling at constant volume, which is the cooling of the exhaust gases. Okay, and that's where the energy leaves the system. Okay, so constant volume here means that I think work is going to be 0, right? From B to C and D to A, the work done should be 0, right? Because it's constant volume. All right. So now what we'd like to do is to calculate the efficiency of our Otto cycle. That's what we want to do. So given a system like this, what would the efficiency look like? That's what we want to do. Let's see if we can keep all this stuff on the screen at the same time, because there's a lot of stuff we want to keep together here. All right. First thing to do is to say that for the processes where heat is coming into the system, where we know that, let's say, for BC and for DA, that's the order, right? In both of these cases, we have constant volume, right? When we have constant volume, that means that, what is it? Q is equal to delta U, right? And for constant volume processes, we can say that the amount of heat that gets transferred is the number of moles multiplied by the specific heat at constant volume and then multiplied by the temperature difference, right? In this case, that's going to be for the BC, where the hot energy comes in. We can say that QH should be equal to N times CV times. So temperature difference from point B to point C should be TC minus TB. Whatever the temperature at point C is, minus the temperature at point B. That's what QH is going to be. We can do the same thing for Q cold, which is going to occur along the process DA, where the QC leaves the system. And we can say that QC is going to be equal to N times the specific heat at constant volume for our gas, multiplied by the temperature difference at that location, which is going to be, we're going from D to A, so TA minus TB. Okay? And we would guess that the QH is going to be a positive number, and this is going to be a negative number, right? All right. Then we can say that our definition for efficiency was that we take QH minus QC, because that's the work done, right? And we divide that by, what was it, QH or QC? What goes in the denominator here? QH, that's right. Because this is the energy input, right? And this is the energy output, right? This is like output. If you want a way to remember, this is output over input. Because that's what efficiency is, after all, right? How much do you get out versus how much you put in? In whatever system you're talking about, that's always how it's going to be defined, whether it's a thermodynamic system or mechanical system or whatever you're looking at. So, all right, so how do we write this one? So now, there's another way to write it too, though, right? Which was that we could also write it without the absolute value symbols as QH plus QC divided by QH. Because, in our case, these numbers are naturally going to be positive or negative just based on the temperature differences. So, let's plug those in. So we'll have N times CV times TC minus TB. That's the QH right here. Plus N CV T. Wait a minute, hold up here. Something's wrong. That's a D. It's A minus D. Sorry about that. I'll put it in a different color so it's clear that I made a change. That was a D right there. Sorry about that. All right, N CV. We're gonna run out of room here, so we're gonna have to scroll down, and we're just gonna have to take this with us. So we'll make a copy of this one. We'll just scroll down and we'll just put it over here. All right, there we go. Okay, so N CV. Now we have TA minus TD. And we end up dividing this whole thing by QH, which was NCV TC minus TB. Okay. And of course, we can cancel a bunch of stuff out, and we end up getting that our efficiency now is just equal to a bunch of temperature differences. We have TC minus TB plus TA minus TD divided by TC minus TB. Okay, now what we can do is we can use our information about adiabatic processes and temperature and volume and how they're related to each other. So to remind you how that was from our previous chapter, when we were talking about adiabatic systems, we can relate, where is it here? Where's the adiabatic process? A to B and C to D are adiabatic, right? We know that for an adiabatic process, that, what was it? T times V to the gamma is a constant, right? T times V to the gamma is a constant. Do you all remember that from last time? TV to the gamma. Wait, was it TV to the gamma minus 1 or TV to the gamma? I think it's gamma minus 1, actually. TV to the gamma minus 1, excuse me. It was the PV to the other one was this one, PV to the gamma. That's the other one, right? But when it's temperature, it's TV to the gamma minus 1. Does that look right to you all? You all remember that from last time? Went through this whole derivation. Yeah. Okay, so since that's the case, we can relate TA and TB, because that's an adiabatic process, right? So we can say that TA VA to the gamma minus 1 should be equal to, so now we go to the other point, which is B here, TB VB to the gamma minus 1. But in this case, the volume at point A is RV. R, again, was the compression ratio. And the volume at point B, we can just call, V to the gamma minus 1, right? It's V. And I believe now we can rewrite this just as, because there's a v to the gamma minus 1 and there's a v to the gamma minus 1, those just cancel, right? So now we just have Ta times R is equal to Tb. And we can play the same game in going from C to D, where I'll just write this down. You tell me if it seems reasonable. If Tc is the one that is V, so it should be over here actually. This should be Tc, and then the one that's at the R is Td. Oops. Td. We can just say likewise to avoid having to go through it. So we can save a little bit of time. So do those two seem logical to you? Oh, whoops. I made a mistake. Sorry, you're all probably wondering what happened to this thing. There should also be a gamma minus 1 up here and a gamma minus 1 up here too. Sorry. Okay, now that I fixed that, does this seem reasonable to you all? Okay, let's put everything together then. So now coming back to our efficiency equation, for Tc, where we see Tc, okay, what do we want to do here actually though? We already have Tc minus Tb in the denominator, so actually I think all we want to do is to get rid of I guess it doesn't matter what we get rid of, does it? Okay, in the interest of not having to use negative exponents, let's just use these and directly replace them. So what do we have? We have Tc is equal to Td r to the gamma minus 1 minus Tb, and Tb is equal to Ta r to the gamma minus 1. So all I've done here is I've just replaced Tc with this, Tb with this, right? Using our equations here. And then Ta and Td stay the same. So plus Ta minus Td divided by Tc gets replaced with Td r to the gamma minus 1, right? Td r to the gamma minus 1 minus Tb, and Tb is Ta r to the gamma minus 1. And now I think we can factor out a Td minus Ta from everything, right? Because there's a Td minus Ta here times r to the gamma minus 1, and then plus 1, right? Divided by Td minus Ta multiplied by r to the gamma minus 1. So that's like a double factor. I hope that doesn't confuse you all too much, but I guess I could have done 2 steps. But hopefully you all can follow that algebra. We're kind of running short on time, and I'd like to at least get to the result. Did I drop a minus sign somewhere? Oh. You know what? Let's just do this step. Because I made a mistake, and I think that's evidence that it's too hard to figure out what's going on here. Let's put the intermediary step in here, because I made a mistake, and you'll see what the mistake is when I do it. This is supposed to be a minus sign, but we'll change it when we fix it. All right, so what's the second step here? The second step would be to say E equal to. So there's an r to the gamma minus 1 and r to the gamma minus 1 here, so we can factor out r to the gamma minus 1 out of the first 2 terms, so you get Td minus Ta, okay, plus. Now this says Ta minus Td here, but I can rearrange those, right? And I can write them as Td minus Ta, as long as I also multiply by -1, right? That doesn't change anything. And then in the denominator, obviously, we can do Td minus Ta, and we can factor an r to the gamma minus 1 out of both of those. So that means that I made a mistake here, and this should have been a minus sign. Sorry about that. There we go. I think everyone should be able to follow those steps of algebra now. Finally, then, of course, we can just make cancellation here. And now we get down to a very simple result, which is that our efficiency, which is right over here, is now equal to r to the gamma minus 1 over or r to the gamma minus 1 over r to the gamma minus 1, which we can simplify even further, as 1 minus 1 over r to the gamma minus 1. But 1 over r to the gamma minus 1 is the same thing as 1 minus r to the 1 minus gamma, I think. That's probably the easiest way to write it. But either way works. If the book writes it on the left way, I would write it on the right way. Whatever you want to do. Either one of those. I apologize that my r's kind of look a little bit like gammas. But this down here is an r. And the gammas are those things up there. And there's our efficiency. It's related to the compression ratio. And it's related to the quantity gamma. So if we're using like air, what was the gamma value for air? I think for air it was like 1.4. Right? So if we use that and we use a compression ratio that's equal to 8, for example, then we can calculate exactly what the efficiency is. If we just do 1 minus, what do we get there? 1 minus 1 divided by 8 to the 0.4. You get 56%. So if you use those values there, you end up getting an efficiency of about 56%. You can check that yourself. Okay? Anyone have any questions? How much time do we have left? 7 minutes, I think we have left. The book also talks about something called the diesel cycle. Let's see if I included that over here. I think I did. And I think what we want to do is we want to do this problem. That's really what I want to do before we end class. Maybe I didn't put the diesel cycle on here. Maybe I'm wrong. So let's just do this problem then. There it goes. Okay, so this isn't related to the Otto cycle. I don't think the book has any problems on the Otto cycle, but you'll see problems in your homework involving this right here. This is just another problem that I wanted to do that takes a PV diagram and asks us to do a this calculation here basically for it. And I'm pretty sure we have all the things we need to know about how to solve this, unless I'm crazy. I think we have all the information we need. Okay, so it says the PV diagram in figure 20.5 shows a cycle of a heat engine that uses 0.25 moles of an ideal gas with gamma equal to 1.4. Process AB is adiabatic. So right here, this is adiabatic. Oops. A to B. This is from your textbook too. It's problem 20.5 if you want to go find the problem. It says to find the pressure of the gas at point A, how much heat enters this gas per cycle and where does it happen? How much heat leaves the gas in a cycle and where does it occur? How much work does this engine do in a cycle? What is this thermal efficiency of this engine? Okay, so this kind of connects together some ideas that we learned in the last chapter to the efficiency ideas that we learned in this chapter. Okay, so what do we know? We have N equal to 0.250 mole. We have gamma equal to 1.4. And the first thing that it tells us to do is to find the pressure of the gas at point A. We know that the pressure is 1.5 atmospheres here. We know the volume is 0.002 meters cubed and 0.009 meters cubed here. And we want to find the pressure at point A. How can we do that? How can we find the pressure at point A in this problem? Any ideas? That's right. Since A to C is adiabatic, that means that the quantity PV to the gamma needs to be constant, at least along the process A to B. So that means that if we know the pressure at point A, which we're searching for, times the volume at point A to the gamma, that should be equal to the pressure at point B times the volume at point B to the gamma. So we can find, we know the pressure at point B, it's given, And we need to find the pressure at point A. So let's solve this. So PA should be equal to PB times the ratio of VB over VA to the gamma. So that's going to be 1.5 atmospheres times the volume at B is 0.009 meters cubed. And the volume at point A is the same as the volume at point C right here, 0.002 meters cubed. And then we raise that to the gamma power. Gamma was 1.4, and this is going to allow us to find the pressure at point A in atmospheres. So do that real quick. 9 halves is 4.5. So 1.5 times 4.5 to the 1.4. So I got 12.32. Do you all agree? It's good that it's larger than the pressure at the other point. Alrighty. Part B says, how much heat enters this gas per cycle, and where does this happen? All right. Well, it seems to me that heat has to be coming in on this side, right? If the pressure goes up substantially without the volume increasing, right? The volume's constant. If the pressure goes up substantially, then I would say that the heat has to be coming in here, right? So along AC is where the heat is coming in. And now we want to find how much heat actually enters the process. How can we do that? How do we find the amount of heat that comes in? We kind of used it in, if you're lost, we started this derivation here by using it up here at the top. We can use the molar heat capacity, right? So I'm going to speed this along here because I don't want to keep you all too long. Yeah, NCV delta T, exactly. All right, so NCV times delta T is what we're going to need to find the amount of heat that comes in. Now, in order to do this, we're also going to need to know what the temperatures are, right? So we have QH then is equal to N times CV. I'm pretty sure we can get CV. You all tell me if this is right or not. If CV is equal to something like R over gamma minus 1. Does that sound right to you? It can't be gamma minus 1 over R, so I think this is what CV is. Check back in your notes, tell me if that's wrong or not. So N times R divided by gamma minus 1, that's what CV is going to be, times delta T. So this is going to be the temperature at point C. No, TA minus TC, right? Final minus initial. But we're now going to have to come up with the relationship to find TA and TC. And for that, are we going to use this one? I don't think we can, because the volume is constant. And it's not an adiabatic process, right? What is it, Umair? What's it equal to, buddy? Help us out. Oh, it does equal that. I don't know why I saw it doesn't. I just assume I'm wrong always. Okay, so we can't use this one, right, to find temperatures, right? What can we use to find temperatures? Temperature A and temperature C. This is actually simpler than you probably think. What is it going to be? Ideal gas law, exactly. So we know that TA should be equal to the pressure at point, so it's PV over NR, right? PV over NR. So pressure at A, volume at A here, and then TB is going to be, no, TC, we're doing TC, right? Sorry, TC is going to be the pressure at point C times the volume at point C, which happens to be the same as the volume at point A, divided by N times R. So we can plug those into our equation here. So we'll get QH is equal to NR over gamma minus 1 times TA minus TC is going to be PA. I feel like we're going through a derivation that we actually did last time. PAVA minus PCVC divided by n times r. And now, luckily, these cancel actually, so we don't even actually put those things into our equation. So we get QH is going to be equal to, the volume at A and volume at C are the same, so it's really going to be PA minus PC over gamma minus 1 times our volume, which is going to be the same for both of them. So now we just plug in our numbers. We have to convert these things too, so we'll do the conversion with the calculation. So the pressure at point A was 12.3 atm. The pressure at point C was 1.5 atm. We multiply that times the volume, which is the same in both cases, which is 0.002 meters cubed. We divide that, there we go, and then we just divide that by gamma minus 1, and gamma minus 1 is 0.4. So QH is equal to, and we got to multiply that by, there's no room. That makes room here. The number of atmospheres in a Pascal, so 1 atm is 1.013 times 10 to the 5th PA. So we get that, so then we get QH is equal to, we have to be over time now, right? We're going over. Nothing I can do about it. If you need to go, you can go. I'll, of course, upload this. So that minus 1.5 times 0.002 divided by 0.4 times 1.013E5. Tell me if you get the same number. I got 5480. That's a pretty reasonable number, actually. I think it's believable that that's the right answer. If we got something like 54 million, I would have been kind of worried. Okay, that's only part B. We got 3 more to do, but I think we've kind of gotten through some of the harder parts of it now. Part C says, how much heat leaves this gas in a cycle and where does it occur? Part D, how much work? And then finally, we'll find the efficiency. So how much heat leaves this gas per cycle? Part C. I think that's going to be here, right? Because if A to B is adiabatic, it can't be there because that's where Q is equal to 0, right? So it has to be BC. So from B to C is where QC is coming out. And along that process, we have cooling occurring because the gas decreased its volume at constant pressure. How do we want to find the amount of heat that left, though? I think we can use this, right? QC should be... It's a constant pressure process, right? It's a constant pressure process. I think it's going to be something like this. Let me show you where I'm going to get this from. So we know that... We just want QC, right? What do we know? We know delta U is equal to Q minus W. And delta U is equal to Q. What I was thinking was we could just do this. But we only need the heat, right? I think this piece is just going to be what we call QC. If we just do NCP delta T. Does that seem reasonable to everyone? Use the molar specific heat capacity, the molar heat capacity at constant pressure, where we know that, what is CP equal to? So CP is related, I think it's like CP plus R is CV, right? No, that can't be right. Because the pressure ones were bigger, right? It's R plus CV, right? I think this is what we have. And that means that it's R plus R over gamma minus 1. I'm getting kind of worried. Is this correct? Can you all verify that for me? Is that yes an answer to this or something else? No, probably not. I have to go back in the book. I don't memorize this stuff very well. It's from the last chapter where we talked about this stuff there, so it shouldn't be hard to find. Was it 2 chapters ago? Here we go. CV is 3/2 R. No, it was not in this chapter. It's chapter 19, I guess. Where did we talk about this? CV and CP. CP is CV plus R. Okay, I got it right. And CV was R over gamma minus 1. So there we go. That's correct. Okay, so we can say QC then is going to be equal to the number of moles times the specific heat at constant pressure times... Now we're going to need the temperature difference between these 2 points right here, which is going to be final minus initial, so TC minus TB. And we can plug everything in now, so QC is going to be N times CP. CP is, we'll just say R plus R over gamma minus 1. We can obviously factor an R out of that. For our temperatures here, again, we're going to have to use the ideal gas law. So we'll have temperature at point C is this one, PC VC over NR, and that's going to be minus temperature at point B, which will be PA VA, not A, it's B, right? It's going to be TBVB over NR. We can simplify that a little bit because there's an NR in every term, so we get QC is equal to, cancel out all the NRs. This first thing is going to be 1 plus 1 over gamma minus 1 multiplied by pressure at C. These are the same. The pressures are constant in this case, so it's going to be pressure multiplied by the volume at point C minus the volume at point B. And we can plug everything in now. So we get QC is equal to 1 plus 1 over 0.4 multiplied by our pressure, which in this case is 1.5 atmospheres along this process from here to here. And then the volume at C minus the volume at B is going to be 0.002 minus 0.009. So 0.002 meters cubed minus 0.009 meters cubed. And we're actually going to get a negative number out of this, which is really good because we want the number to be negative because QC is supposed to be negative. And again, we have to multiply by the ratio of 1.013 times 10 to the 5 pascals divided by 1 ATM. This gives us I get negative 3722. This is really good because it's, again, another reasonable size number. And it's smaller, absolute value-wise, than QH, which is exactly what we would expect. We'll just say 3723 joules. Do you all agree? This is a really good problem. You have to take it, like, we have to use so many different things that we've learned about so far to actually get this to work out right. Okay. So now we have QH and QC, and D was how much work does the engine do in a cycle. That's really easy to do. To find the amount of work done in a cycle, we can just say the work done is going to be equal to QH plus QC, or the absolute value of QH minus the absolute value of QC. Either way you want to do it. So this is going to be 5480 joules minus 3723 joules. So that plus, here, 3 plus 5480. So we get the work done per cycle is going to be 1757 joules. That's W, the work done per cycle. And I think finally all we have to do is calculate efficiency, right? Thermal efficiency E should be equal to 1. There's two different, I think the easiest one to remember for me is just always work divided by QH. It's just the simplest one to remember. So if we take 1757 joules and we divide by QH, which was 5480, we get an efficiency of, sorry, we went really quite over today, but I think this is a good problem to do. I think it'll help a lot with doing your homeworks and stuff like that. So you can see kind of all the things that are involved in solving these type of problems. You got to kind of really pull together a lot of stuff we've talked about. All right, so we didn't actually get to the statement of the second law of thermodynamics today, but I'm going to show you what it is just real quick. because that's where we'll start class next time. And this is it. I'm just going to throw it up on the screen here, and we'll finish with that. This is the statement of the second law of thermodynamics. It says that it is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state in which it began. Another way of saying this is that it's impossible to construct a heat engine that is 100% efficient. All right, that's where we're going to stop today. We'll talk about that next time. And we have a lab this week. It is F-3. So if you're part of the first group to go, then you'll be showing up on the first half of the alphabet. Will be showing up on Wednesday, I guess, right? So I will see you all then, and have a good day.